Okay, hello physics class. Hope you guys are doing alright. I'm going to try to explain chapter 7. So again, it's really important to read the book. I'm really emphasizing reading the book. He explains things really well. Do that as best you can. I know these are crazy times, but hopefully you and your families are doing alright and you can find some time to get some physics in. So, okay, I'm going to go over chapter 7, and the whole idea of chapter 7 is momentum. And the idea with momentum is it's basically how hard it is to stop something, and it's just equal to the mass of something times the velocity. So pretty darn easy formula. It's often given the letter P because M is taken already by mass, and so the letter P isn't really taken, even though it has nothing to do with momentum. So we can write the formula that P equals mv is momentum, and the units for momentum, them are mass, which is kilograms, times velocity, which is meters per second. So, which does not have a name. It's not like newtons, which has a name. It's just kilogram meter per second. So we'll just always make sure we're using mass in kilograms and velocity in meters per second, and that's just momentum units, so there's no word for that, so it's kind of awkward. But, okay, now to change something's momentum, you have to exert a force, and not just a force, but you have to exert a force for a little while, and they call that the impulse. So the impulse is exerting a force for a little bit of time, call that little bit of time delta t. And that changes something's momentum. When you change something's momentum, you typically don't change its mass. That stays the same. So you change its velocity. So the mass times change in velocity. So that's what's called the impulse formula. Impulse is force times time, and that's how you change something's momentum. You exert a force for a little while. The longer you exert the force, the more the velocity is going to change, right? The longer your engine's on running, the more you're going to speed up. The longer you push someone on a swing, the faster they're going to go. So it makes sense. Force times time, not time you exert the force, is a mass times its change in velocity. Many times we'll assume it starts from stopped. So if you want how fast it's going to go, how big a force for how long times is equal to its momentum that it has. And then the last big idea in this chapter is that in collisions, a lot of times, momentum is conserved. As long as it doesn't go to the earth or something, momentum is conserved. So the momentum before, so P for momentum, the momentum before the collision, before something happens, is equal to the momentum after something happens, as long as there's no outside things interacting. And many times that works. So momentum before is equal to momentum after. So you'd say that the momentum before, so maybe m1 v1 before the collision is equal to m2 v2, the momentum after the collision. Now, yeah, so, and you can have more than two things. I guess in this case, we could have, yeah, this doesn't really make sense because why would M1, M2 all be the different? But a lot of times you have two things happening. So if we had a ball, here's our M1, and it's scrolling along by itself, and it hits another ball, which is M2, and they both go off in different directions. So now our M1 is going off this way. We'd say the momentum of the first one, because it's the only one moving in the beginning, is equal to the momentum of the second one, because it goes rolling off, plus the momentum of the first one, which is a new velocity, so we can call that m1 v1 with little prime or something. So momentum before, which is only one moving, is equal to the momentum after. Now we have two things moving. M1 is still moving with a new speed, and M2 is now moving when it wasn't before. So that's kind of how you apply conservation of momentum. Momentum before is equal to momentum after. Okay, so that's the general idea. When you're doing problems, like a typical problem is, let's say you have a tennis ball and the mass is 1 kilogram, which would be one heck of a heavy tennis ball. And let's say that you exert a force of 100 newtons on it, so that's our force, and let's say that you exert that force for, delta t is 0.1 seconds, So you hit the ball for 0.1 seconds. You're exerting 100 newtons for only 0.1 seconds because it doesn't hit the racket very long. So now, how fast is the ball going to leave your tennis racket? So we write down the impulse formula. F delta T is equal to M delta V. Assuming the ball stops, it starts from stopped, which you typically do, we want to know the change in velocity. What's the change in velocity? So the change in velocity is equal to the force times the time divided by the mass. We just plug in the numbers. 100 newtons times 0.1 seconds. Put that in parentheses, divided by the mass, which I said was 1 kilogram, which is a very heavy ball. And let's see, 0.1 times 100 is 10, so that would be 10 meters per second. So it would leave your tennis racket at 10 meters per second. So that's kind of the idea of doing a problem like that. Now the other typical problem that you'll run into is if a collision problem. So let me do one of those really quickly. So let's say we have a 2 kilogram mass of clay and it's moving this way at 3 meters per second, and it hits a 5 kilogram mass that's not moving, and they move off together. So this is before, and afterwards we have basically a squished together 7 kilogram mass, and how fast is it going to be going? That's often what we want to know. So 2 going 3 hits a 5 that's not moving, they stick together and make a 7. How fast is that moving? So what we do is we say the momentum before, which is m1 v1, which is this, is equal to momentum afterwards. So the momentum afterwards is the new mass times its velocity. Okay, well we know m1 v1, that's 2 times 3. And our new mass is 7, because they stick together, so it's 7, and so then times the velocity. The only thing we don't know is the velocity. So the velocity is, this is 6 divided by 7, and we're losing meters, so it's meters per second. So, not so bad. That's using conservation momentum. Momentum before is equal to momentum after. Since we hit something, the mass changes, so it's going to be moving a little bit slower, which it is. It starts off, this one's moving at 3, that one only goes at 6/7. So anyway, that's the idea for how you do these. Hopefully that helps out. Again, I think I said you could try to do numbers 19 through 27, 23 through 27 are more questions, while 19 through 22 are problems, plus of course the multiple choice problems. So let me know how that goes, and hopefully you can find some time to get all this done, and then you can take pictures of your work and send it to me so I can give you credit for it. So, okay, we'll be in touch. Bye.